Section 1 Introduction. Over the past few years, large neural networks built on the transformer architecture have shown remarkable performance in understanding and generating language. Progress in these transformer-based models has been achieved by increasing the model size, expanding the amount of training data, improving the quality of the training data, and using sparse activation structures in the models. Among these efficient language models, there's a trend towards enhancing the efficiency of attention layers with methods such as low-rank approaches or approximations. Nevertheless, recent research has highlighted that the dense feed-forward layers can often be the major source of computational cost, particularly when the model is large and dealing with common sequence lengths up to 2048. To further enhance computational efficiency, like total floating point operations, FLOPs, used during training to reach convergence, mixture of experts, MO, with sparse gating has gained popularity. These offer the model a larger capacity to improve performance without increasing computational cost. Sparsely activated models also provide better specialization by training different expert components on different data distributions, using a routing function, without reducing the effective training time for each expert. The MO models in this field typically use uniform transformer blocks or a combination of dense and sparse layers, along with a fixed top K routing. Building on the approach of layer-wise architecture stacking found in efficient net and layer reordering in the sandwich transformer, we suggest a non-uniform architecture with sparsity that doesn't strictly follow the layer interleaving of the original transformer model. We allow the search space to compose different sublayers and different orders, trading off architectural regularity. To improve scaling, we introduce sparsity in the search space with a sparsely gated feed-forward layer and MO layer, paired with various gating mechanisms. Our findings show that optimizing the architecture, sparsity, and routing mechanism in sparse layers is key to achieving nearly ideal log-scale quality scaling. Our model, which we call Brainformer, scales much better than GLAM, a manually designed sparse transformer. Brainformer consistently enhances training perplexity while maintaining a steady example rate even when increasing model capacity. In contrast, GLAM's example rate suffers when scaled up. We use the MO layer as a general method to make the model more sparse, but any conditional computation method can be incorporated. We use a simple evolutionary search to uncover the best attributes, such as the optimal ways to interleave layers, capacities of layers, when to combine layers, and when to specialize layers with MO modules. For easier scaling, we propose a block-wise sublayer grouping. This method allows us to stack a variable number of blocks to create models of different scales, as demonstrated in our model we call the stackable Brainformer. Our results have shown that this approach is effective at various model scales. Section Summary. The paper discusses the use of sparsely activated models to reduce computational cost and improve specialization in large neural networks derived from the transformer architecture. The authors propose a non-uniform architecture with sparsity and a sparsely gated feed-forward layer coupled with different gating mechanisms to achieve near-perfect log-scale scaling in quality. They also introduce a block-wise sublayer grouping for ease of scaling, which has proven effective in their evaluation at multiple model scales. Section 2 Related Work. In this section, we discuss related work, which includes advancements in large language models, sparsely activated models, and non-uniform architectures. Large language models have consistently shown strong results in various natural language processing tasks. The key to their success lies in scaling up their capacity and increasing the number of tokens used during training. This approach has not only significantly improved the performance of these models, but also proven effective in computer vision architectures. Secondly, sparsely activated models use a technique called conditional computation. This allows for an increase in the capacity of deep neural networks without a corresponding increase in computation. In simpler terms, these models activate certain parameters and computational processes as needed, depending on the input. The decision to activate these components can be either binary or sparse and continuous, and either stochastic, random, or deterministic, predictable. Particularly in multi-device settings, sparsely gated mixture of experts, MO, models have shown significant improvements in model capacity, training time, and model quality. Numerous MO architectures, including the switch transformer and GLAM, use a token-based gating system. These architectures often include an auxiliary loss to mitigate the issue of load imbalance. More recently, advanced gating functions have been developed to further address load imbalance, increase speed, and improve generalization. Finally, non-uniform architectures such as the efficient net have leveraged layer diversity to reach state-of-the-art performance. Instead of introducing new operators or blocks of operators, efficient net optimizes layer compound coefficients, which allows the model to scale effectively. This diversity leads to a model that is more than 8 times smaller and over 6 times faster during inference. The sandwich transformer introduces a non-interleaved, non-uniform architecture for language modeling tasks. However, the sandwich reordering pattern doesn't always guarantee improved performance for every task. The residual MO model approaches this by factorizing the weights into an input-independent core and an input-dependent residual. This achieves results comparable to high-performing MO training, while only adding a small additional training cost compared to lower-performing non-MO training. In our work, we're inspired by these advancements but aim to further improve scaling and generalization through automatic model discoveries. Section Summary. Large language models have shown success in natural language processing tasks by scaling up model capacity and training tokens. Sparsely activated models, such as sparsely gated MO, have demonstrated improvements in model capacity, training time, and quality with gating. Non-uniform architectures, like efficient net and residual MO, have also shown promise in scaling and generalization. This work aims to improve scaling and generalization through automatic model discoveries. Section 3 Method.3 Methodology 3.1 Developing our model components. We can utilize different types of computation factorization to decrease computation time or speed up the process without compromising the quality of the model. As per previous research, using low-rank and multi-expert layers are two primary ways to factorize a matrix multiplication. Both methods cut computational operations, or flops, in half without reducing the model's capabilities. When we're crafting an efficient neural network, we can fuse low-rank and multi-expert elements, then stack them to create unique, efficient model structures. Adding a temporal mixture layer, like attention, GMLP or MLP mixer, which maps out the causal links between tokens, evolves the network into a multi-expert transformer variant. However, designing an effective network doesn't mean we have to stick strictly to a uniform model architecture, as depicted in the final figure of previous research. By carefully choosing the types of layers, the order in which they're stacked, and other layer-specific parameters, we can improve model quality, training efficiency, and scalability. This drives our exploration towards a more training-efficient architecture using low-rank and multi-expert compression techniques with coarse-grained sparsity. Section Summary. The section discusses the use of low-rank and multi-expert layers as methods for factorizing a matrix multiplication, which reduces computation cost without sacrificing model capacity. These methods can be combined and stacked with a temporal mixture layer to create a multi-expert transformer variant. The author suggests that constructing an efficient network does not require uniformity in model architecture, and careful selection of layer types and hyperparameters can lead to higher quality, training efficiency, and better scaling. Section 3. In Section 3.2, we discuss our blockwise architecture, which is primarily influenced by the compound scaling approach of efficient net. Our aim was to make the process of scaling easier, hence we chose to work within a blockwise search space, unlike the standard practice of stacking layers uniformly. We've devised a universal layer represented as a function y_i equals f_i x_i, where f_i is an operator chosen from a set of operations. This set comprises self-attention, sparsely gated feed-forward, also known as MO, and dense feed-forward sublayers. Input x_i takes on a tensor shape of b, l, h, where b denotes the batch size, l represents the sequence length, and h is a variable model dimension. This model dimension h can vary between 75% and 150% of the standard model dimension h_model_dim. By tuning the model dimension, we can create more versatile network topologies using a variety of factorization methods. This allows us to create models with wider hidden dimensions or models with many experts where each expert has a narrow focus. In contrast to the usual simple, uniform transformer block, a Brainformer block is a complex block N that is defined by a sequence of composed layers. We can then stack as many Brainformer blocks as necessary to create a desired model. The goal of our search is to find the best layer architecture, f_i, and scaling multipliers for multiple internal model dimensions that minimize perplexity. We use a table to outline the search space within a Brainformer architecture, and then we illustrate the two phases used to find compute-efficient Brainformer models using figures and an algorithm. During our search, we sample block architectures from the search space and train them using a proxy training task. In this task, a smaller 100M32E architecture is created by stacking the sampled block 3 times, matching the number of layers in a baseline GLAM architecture. We also employ early stopping during proxy training, where models that aren't promising are stopped early due to either exceeding the time limit for inference or failing to meet the perplexity constraint at 25% of the maximum training steps. Once the search phase is complete, the top K block architectures with the highest rewards are evaluated at multiple scales. In our evaluations, we first increase the model dimension and hidden dimension by factors of 2 and 4 to create block S1 and S2, aiming for 1B and 8B model scales respectively. Next, we stack block S1 and S2 to create 1B64E and 8B64E model variants. We determine the number n in the algorithm mathematically according to the total number of active parameters required by the model. Lastly, we compare our findings with baseline architectures at various scales in our final evaluations. Section Summary. The Brainformer architecture is a block-wise search space that allows for more flexible network topologies by creating a generic layer as a function with operators selected from self-attention, sparsely gated feed-forward, MO, and dense feed-forward sublayers. The search objective is to find an optimal layer architecture and model scaling multipliers that minimize perplexity, and a regularized evolutionary search algorithm is used to sample block architectures from the search space and train them using a proxy training. The top K-block architectures with the highest rewards are evaluated at multiple target scales to create 1B64E and 8B64E model variants. Section 3. We're addressing the question of how to fairly compare different types of models used in natural language processing. Typically, these comparisons have been based on a fixed model size and the number of training steps or tokens used, meaning that we're comparing models by changing the model parameters but keeping the number of training steps constant. However, in real-world scenarios, we often have to work within certain constraints like time, computational resources, and desired output quality. When considering these factors, a straight comparison based on total model parameters doesn't quite work. It's especially not equitable when we're looking at different model architectures or families of models. For instance, such a comparison may unfairly disadvantage models that have more parameters but use fewer computational operations, such as those that use sparse activation. The GLAM paper proposed a different way to address this issue, by conducting a study focusing on the activated memory, which is a proxy for computational cost, instead of the total number of model parameters. This was done with a constant number of training tokens. However, this approach still has its limitations as smaller models might benefit more from extra training data and perform better than larger models given the same overall training cost, measured in GPU or TPU hours. This led to the Chinchilla paper, which suggested a method called compute-efficient scaling. This technique takes into account both the model size and the number of training tokens, but keeps the overall computational cost constant. We agree with this approach, but we also believe it's important to consider changes to the model's architecture when seeking the most efficient designs. Specifically, we're comparing models based on a fixed training cost and model inference time, allowing the search algorithm to balance between model size and the number of training tokens. Section Summary. Previous studies on NLP model scaling typically compare model qualities while fixing total parameters, which may not be fair when comparing across model architectures and families. The Chinchilla paper suggests compute-efficient scaling, which varies both model capacity and training tokens at a fixed computational cost, allowing for a fair comparison. In our search for efficient model architectures, we compare models with a fixed training cost and inference time, enabling the algorithm to trade off between model capacity and training tokens. Section 3. In this section, we'll delve into our method of training time-constrained search. We set a specific limit on the wall clock time for each model search attempt. This means we're promoting the discovery of models that can train more quickly. Our goal here is to uncover model architectures that can produce more accurate results, but within a fixed training budget. This budget refers to the total time we have available for training, which is calculated by multiplying the number of chips used by the number of hours allotted for training. To put this into context, in an evolution search, there's a control mechanism that aims to reduce the validation loss, a measure of the model's errors, before any actual training happens, while also adhering to a predefined limit on inference time. Our base model is a type of transformer architecture with 100 million parameters, which we'll refer to as the vanilla transformer architecture. During each trial, we maintain a fixed wall clock time for training, which helps us balance out faster models by allowing them more training steps. Through our experiments, we've observed that keeping the training time fixed, while also managing the inference time constraint, has resulted in models that both train quicker and produce higher quality results. Now, let's talk a bit about our mathematical formulation. We have an objective function which we aim to minimize. This function depends on various parameters, including the model's architecture and its components, such as depth, type of activation functions, and others. This function is defined in a conditional manner. If a certain part of the model, f, corresponds to an attention component, we use one set of parameters. If it corresponds to a feed-forward network component, we use another set, and so on. The output of our model, given an input x, is produced by applying each part of the model, from f1 to fk, to the input in succession. The step time, or time taken per step by our model, must not exceed a baseline time limit. By constraining the model's operation within these limits, we're trying to ensure that it trains as efficiently as possible while still producing high-quality results. Section summary. The authors use a fixed wall clock time for each search trial to encourage models with faster training convergence. The objective is to find model architectures that yield higher accuracy with a fixed training budget. They find that fixing training wall clock time while meeting an inference time constraint yields models with faster training convergence and higher quality. Section 4. Token-based routing versus expert-based routing. In our exploration of different routing methods in the mixtures of experts, MO, literature, we focused on two main categories: token-based routing and expert-based routing. Our goal is to demonstrate how these routing strategies can alter the best model architecture, particularly when sparse activation layers come into play. To visualize this, consider a diagram where the rows and columns represent unnormalized scores calculated for 4 tokens and 4 experts respectively. These scores are obtained by taking the dot product of each token's embedding with each expert's embedding. Once we've generated these affinity scores between tokens and experts, we then have to decide which experts each token should be directed towards. If we're using token-based routing, our model will select the top k experts for each token. On the other hand, with expert-based routing, it's the experts that select the top k tokens. To get a bit more specific, we've been using a top 2 gating strategy, following the example of models like GS-Hard and GLAM. These models have shown that top 2 gating typically yields better results than top 1 gating. For our expert-based routing, we've adopted the expert choice gating method, which allows us to achieve perfect load balance along with a diverse parameter allocation. There are several methods to calculate these token to expert affinity scores. One possible approach involves creating a trainable gating matrix, denoted as W_G, that can project the input features onto a token to expert scoring space. These scores then need to be normalized, either across the token dimension or the expert dimension. To prevent the model from accidentally leaking information in the decoding stage, we propose normalizing these scores along the expert dimension, regardless of whether we're using token-based or expert-based routing. Section summary. The paper focuses on 2 types of routing methods, token-based and expert-based, to demonstrate how routing strategy can affect the optimal model architecture when sparsely activated layers are introduced. Token-based routing routes to the top k experts for each token, while expert-based routing allows experts to choose top k tokens. The paper suggests using a trainable gating matrix to generate token to expert affinity scores, which should be normalized along the expert dimension to avoid causal leakage in decoding mode. Section 5. Evaluation. Let's now turn our attention to the evaluation process we carried out for our models. We'll begin by discussing the setup of the experiment. We set up a number of different models, focusing on what's known as mixture of experts, or MO models. We compare these to baseline configurations, each with their own unique hyperparameter settings. In one such model, called the baseline MO GLAM, we alternated between 2 types of layers in our model: regular dense feed-forward networks, FFNs, and sparsely gated FFNs, which we refer to as MO layers. To give you a point of reference, we've also provided configurations of dense models that have similar numbers of parameters activated for each token during inference. One such sparse model, labeled as 0.1b, 32e, is configured with a similar number of active parameters as a 0.1 billion, 0.1b, dense model. This sparse model is designed with alternating layers, where every second layer is a 32 expert MO layer. You might be wondering what these terms mean. In the context of this paper, n_params represents the total number of parameters that the model can adjust during training, whereas n_act params refers to how many of those parameters are activated for each token. The latter serves as a rough estimate of the computational cost of a model. Other key terms include L, the total number of transformer layers in the model, M, the model's overall size or dimension, and H, the hidden dimension. After projection in each transformer layer, n_heads refers to the number of attention heads, and d_head is the hidden dimension of each attention head. We performed our training and evaluation on Google's Cloud TPU v4 chips. Models of a certain size, 8 billion parameters, or 8B, required a whopping 512 of these chips for training. The dataset we used for this process was a high-quality set of 1.6 trillion tokens, drawn from a wide variety of sources, representing diverse natural language use cases. It includes a high-quality filtered subset of web pages, as well as smaller corpora of books, Wikipedia pages, conversations, forums, and news articles. As for the actual training, we used a few decoder-only models, utilizing the best Brainformer blocks that we identified in our search. 2 models, named Brainformer1 and Brainformer2, were selected as the best. However, due to limited computational resources, we could only scale Brainformer1 up to 1B and 8B. The training setup followed the guidelines set by GLAM, with a maximum sequence length of 1024 tokens. We applied the Attefactor optimizer with decay rates set to 0 for the first moment and 0.99 for the second moment. The learning rate was kept constant for the first 10,000 training steps, and then was reduced following an inverse square root schedule. Tokenization was handled by SentencePiece, a subword tokenizer, with a vocabulary size of 256,000. We trained our models without dropout since our training corpus was large enough that each sample was encountered only once. When it came to evaluating our models, we concentrated on 2 primary types of downstream evaluations. 1. Fine-tuning performance on 11 selected classification tasks from the GLUE and SuperGLUE benchmarks, and 2. Evaluating the performance on 5 language generation tasks, which were primarily focused on question. Section Summary. The section describes the evaluation setup, dataset, model training, and evaluation of Brainformer models and baseline models. The models are trained on a high-quality dataset of 1.6 trillion tokens and evaluated on fine-tuning performance on 11 selected classification tasks and one-shot performance with 5 language generation tasks focused on question answering. The models are trained using Attefactor optimizer and SentencePiece subword tokenizer with a vocabulary of size 256K. Section 5. In Section 5.1, we examine the performance of our top Brainformer models in comparison to related benchmark models. These include a model architecture search using top 2 gating, termed Search W top 2 feet, and GLAM, a manually designed architecture that employs fixed top 2 gating. We found that the ability to adjust both the gating function and network architecture contributes significantly to the efficiency of model pre-training. As per our findings, our best-performing Brainformer models consistently surpass the benchmark models in several key aspects. Computational cost, which we measure in terms of activated parameters, the speed of training steps, measured as steps per second, and training perplexity, abbreviated as PPLX, within a set number of training steps. When we scale up to the size of 8B64E, Brainformer exhibits more efficient convergence to lower perplexity, demonstrating a speed that is 5 times faster in step time and twice as fast in training convergence, compared to the benchmarks. This performance was achieved using the same hardware setup, which consisted of 512 Cloud TPU v4 chips. Further, when we fix the number of training tokens at 600 billion, the Brainformer shows superior accuracy compared to the benchmark models at an 8B scale. In Section 5.2, we discuss the results of model fine-tuning. Using the same total pre-training duration as the GLAM model, we subsequently fine-tuned our models on 11 hand-picked classification tasks from the GLUE and SuperGLUE benchmarks. At 2 distinct scales, specifically 100M64E and 1B64E, our Brainformers significantly exceeded the performance of the GLAM model, improving average scores by 2 to 4%. Our fine-tuning results demonstrate that Brainformer doesn't merely excel in training convergence, but also shows impressive generalization capabilities when applied to various downstream tasks. Section Summary. The Brainformer top models outperform the baselines in terms of computational cost, training step time, and training perplexity for fixed training steps. When scaled to 8B64E, Brainformer converges faster and achieves lower perplexity than the baselines. In addition, Brainformer also performs better than the baseline GLAM model by a significant margin of 2 to 4% average score in 11 selected GLUE and SuperGLUE classification tasks. Section 5. In Section 5.3, we discuss our results with a technique known as fewshot in context learning. Here, we test the performance of our new approach, Brainformer, in a one-shot setting across 5 different generative tasks. These tasks were based in a variety of fields, including natural questions, trivia QA, web questions, Squad 2, and Lambda. For comparison, we also tested 2 other models with similar activated memory sizes, a sparse model called GLAM and a dense model named Primer. The results showed that Brainformer was superior to both Primer and GLAM across all tasks. There was only one exception. Brainformer performed slightly worse than GLAM in the natural questions task. Notably, although GLAM produced competitive scores, it operated at half the speed of Brainformer. In Section 6.1, we offer a visualization and description of one of our Brainformer architecture blocks. This is no ordinary transformer block, which would usually only consist of an attention layer and a dense feed-forward layer. Instead, a Brainformer block comprises 8 sub-layers and is repeated a different number of times depending on the scale of the task. Specifically, we use 3 repetitions for tasks of a 100 million scale, 6 for tasks of 1 billion scale, and 8 for tasks of 8 billion scale. In a traditional transformer model, a dense feed-forward neural network layer would typically have an expansion ratio of 4, resulting in a hidden dimension 4 times wider than the model dimension. However, in our optimized Brainformer blocks 1 and 2, we use a different approach. We choose a slightly larger model dimension of 1024, compared to the conventional 768, and a smaller expansion factor in the dense feed-forward neural networks and mixture of experts, MO, layers, compared to the conventional 3072. This adjustment makes sense, as the MO layers effectively broaden the network by introducing more experts. In the MO layers, we use a gating function called the expert choice with a capacity factor of 1 in Brainformer block 1. This results in a very sparse network where each token, on average, is routed to a single expert. Even though this setup is much faster in terms of step time, block 1 requires more training steps to ensure good quality, thereby using more training data. Considering this, we also selected another potent candidate, Brainformer block 2, which utilizes a larger capacity factor in the MO layers. Though this second block is slightly slower in step time, it achieves good accuracy with fewer training steps, making it more data efficient. Section summary. The paper compares Brainformer's one-shot performance on 5 generative tasks with 2 other models, GLAM and Primer, and finds that Brainformer outperforms both models by a large margin on all tasks except for NQs. The Brainformer architecture block is visualized and contains 8 sub-layers, with optimized dimensions and expansion factors in the dense FFNs and MO layers. The search algorithm picks a gating function with a capacity factor of 1 in Brainformer block 1, resulting in a very sparse network, while block 2 has a larger capacity factor and is more data efficient.